Hi everyone, this is our first video lecture. This is the solution to the practice quiz that I posted earlier this week. It is on homework 7 problem 1, which was problem 10.15 from the text. So let's look at the problem statement. In this problem, we have a wheel with constant angular acceleration of 2.9 radians per second squared. It begins turning from rest, and during some 9-second interval, we note that it turns through 170 radians. We want to know how long the wheel was in motion before we began to measure that 170 radians. Okay. So, as with all physics problems, the first thing that we usually need to do is figure out exactly what the problem is asking us and what it is telling us. We begin by drawing a quick sketch to describe what the problem is doing. So in this problem, we have a wheel that is going to turn through its central body axis. It's going to be turned with a positive angular acceleration of 2.9 radians per second squared. It's going to begin from rest, which means that the initial angle is 0, the initial time is 0, and the initial angular velocity, omega, is also 0. Then later, after it's begun spinning, we don't know what angular velocity it's at, but we're going to measure some change in the angle as 170 rads. And it's going to take a time interval of 9 seconds to do this. But what we want to know is how long was it spinning from when it began until we first started to measure our angular displacement. Okay, so as with all quiz and exam problems, the first thing that I would like you to do is to write down what equations and concepts are relevant to this problem. So we can look back at our problem statement and carefully reading through it, we note that it's telling us that this wheel has constant angular acceleration and that it began from rest. Those are the two key concepts that we need, and they'll tell us what equations we can use. So we write constant angular acceleration, and that tells us that we can use the constant angular acceleration equations that we learned. If you don't recall, the constant angular acceleration equations are exactly like the constant acceleration equations that we had, except instead of x, we're going to use theta. Instead of v, we're going to use omega for the angular velocity. And instead of a, we're going to use alpha for the angular acceleration. So if you don't recall those, we have theta final minus theta initial, or the angular displacement, is equal to the initial angular velocity times time plus the angular acceleration times time squared divided by 2. Secondly, we have that the final angular velocity minus the initial angular velocity is equal to 2 times the angular acceleration times the angular displacement. And lastly, we're going to use the final angular velocity is equal to the initial angular velocity times, or plus alpha times time, okay? And the fact that we began from rest simply tells us that omega initial was 0, theta initial we're going to assume is 0, and time we're going to assume began at 0, okay? Those are our relevant equations and our concepts. There are 2 other equations we could use, but we won't need them for this problem. So let's move on to our first solution. I'm going to give you 2 different solutions to this. I believe the first one is easier to do, easier to understand. The second one requires a little bit of mathematical sophistication, and either solution is appropriate. Either one is fine. It's just, what are you comfortable with? And I realize that some of you aren't quite comfortable with the quadratics. So I'll take you through both. Hopefully you'll learn a little something, and let's go. So solution one, what I want to find is during this interval, I know that the change of angle was 170 rad, and I know that the change of time was 9 seconds. But what I don't know is I don't know what the initial, this is during the later, while we're recording the interval, I don't know what the initial angular velocity here is, and I'm going to call this angular velocity 2. So initially, remember that I began from rest, right? So my initial velocity was 0, and my final velocity 1 is going to be my initial velocity 2. The initial velocity when I began measuring the 170 radian displacement. So what I want to find is I want to find how much time passed from the initial time until I started measuring. So this is what I'm going to call my t. And I need to find this t. I need to find how much time it was spinning from when it began until when I began to measure the angular displacement. Okay. That being said, I need to divide my variables up into 2 distinct times. So there's the initial time. And so initially, I was at rest. My initial angle was 0. My final angle, I don't know. So my final angle here, I don't know. My initial angular velocity was 0. And my final angular velocity, right before I began measuring this 170 radian angular displacement, I don't know what that is either. I do know that alpha was 2.9 radians per second squared. And the time interval from t1, since this is 0, I'm just going to call t1. Okay? Now, during the later time when I'm measuring this change, I know that this was 170 rad. I don't know what the initial angular velocity is, but I know that it was number 1, omega 1. I do not know what this is. I need to figure out. That's what I need to find. Okay. And I know that my time is t2 minus t1, which is 9 seconds. And I know alpha is 2.9 radians per second squared. So those are my variables. From these variables, I also don't know what omega final 2 was, but I don't need it. I'm not going to need these either. Okay. Sorry, I am going to need that. All right, so let's go through our solution. So for the later time, I need to find what the initial angular velocity was. I need to find this and remember that this T2 here is actually our 9-second interval. Okay, so solving this for omega 2t, I get that that is theta final minus theta initial minus alpha times t2 squared over 2. Also note that this omega final at this point is 170 rad. And dividing through by t, I get that this is theta final minus theta initial divided by t. If I divide this by t, I get t over 2. So this is 170 rad divided by 9 minus 2.9 divided by 2 times 9. And that ends up being 5.84 radians per second. So once I've found that, let me insert a new slide. So once I've found that, so I know that my omega 2 is 5.84 radians per second, and that this is actually my omega 1 final. Okay. And I know that omega 1 final is equal to omega naught plus alpha times T1. And T1 is what I want. So this is 0. I get that T1 is omega 1 final divided by alpha, which is 5.84 divided by 2.9, and that gives me 2.013 seconds. Okay, so to go back through this, what we had to find was we had to figure out what the initial angular velocity was when we began to measure our angular displacement of 170 rads. In order to do that, we solved this equation and found that that was 5.84 radians per second. And then for the initial interval, to figure out how long it took to get from rest, from an angular velocity of 0 to an angular velocity of 5.84 seconds, we use this equation and solve for t. Pretty simple, not much to say about it. We use two equations. Our second solution is going to be a little bit more sophisticated, but you may find that it makes more sense. As I said, either one of these solutions is fine. Our strategy for solution number 2 is to find the time it takes from the initial angle until it reaches the beginning, the angle where we first started to measure our displacement. And then also find the time it takes from the beginning, when it started at rest, to the final angle that it made after our angular displacement. And we're going to use the fact that our final angle minus our initial angle was equal to 170 rads. So what our strategy really is here is we need to come up with an equation to describe theta 2 and theta 1, plug them into this equation and solve it for the time. And we'll see how that works. So let's get our variables. So for theta 1, we have theta 1 minus theta initial is equal to t minus t naught plus alpha times t1 minus t naught squared over 2. But we're going to note that the initial angular velocity is 0, the initial time is 0, and the initial angle is also 0. So this goes away, and this goes away, and what we're left with is that theta 1 is equal to alpha divided by 2 times t1 squared. For theta 2, we're going to have the same thing. Theta 2 minus theta initial is equal to omega initial times t2 minus t naught plus alpha times t2 minus t naught squared divided by 2. Again, theta initial is 0, omega initial is 0, and t initial is 0, so that we get that theta 2 is equal to alpha over 2 times t squared. And now, here comes the part where you have to pay attention. There's a key caution here. So from the earlier slide, we saw that theta 2 minus theta 1 was 170 rad. And if we plug in that theta 2 was alpha over 2 times t2 squared minus alpha times t1 squared over 2 is equal to 170 rad. That means that 170 rad is equal to alpha divided by 2 times t2 squared minus t1 squared. Now here's a big caution. Caution. If you naively wrote that the change in angle was equal to omega naught times the change in t plus alpha times the change in t squared over 2, note that this would still be 0. This would, of course, still be our 170 rad, but you would have T2 minus T1 squared, and T2 squared minus T1 squared is not T2 minus T1 squared. So this does not work. Don't do that. You need to do this, okay, and solve it. So this is our equation. And now we need to do a little bit of algebra to get that into something that we can actually use. So let's go ahead and do that. We have 170 rad is equal to alpha over 2 times T2 squared minus T1 squared. Okay, so first of all, let's do this quick algebra. 2 over alpha times 170 is equal to T2 squared minus T1 squared. Note that T2 squared minus T1 squared is T2 plus T1 times T2 minus T1. If you do that algebra out, you get T2 squared minus T1 T2 plus T1 T2 minus T1 squared, okay? So let's plug that in. So we have 2 over 2.9 times 170 is equal to T2 plus T1 times T2 minus T1, but this is 9 seconds, okay? We have that T2 minus T1 was 9 seconds. All right, so T2 plus T1 is equal to 2 over 2.9, 170 over T2 minus T1, which is 2 over 2.9 times 170 over 9. All right, last slide. So what we had was, we had that T2 minus T1 was 9 seconds, and we had that T2 plus T1, if you come back and do this here, this is 13.027 seconds. So we also have 13.027 seconds. And now we can actually add or subtract these two equations. What we're going to do is we're going to subtract them. So we get T2 minus T1 minus T2 minus T1, okay, is equal to 9 minus 13.027. The T2 cancel, and we get minus 2T1 is equal to minus 4.027, and T1 is therefore 2.013 seconds, which was the same answer we got previously using the other method. As I said, this method is a little bit more sophisticated because you had to make sure that you were able to derive this equation correctly. Had you naively done it this way, you would have gotten this answer wrong. You can also go back and check and make sure that the angles work out. We're not going to do that, but that is the correct answer. Hopefully this was helpful. I'm going to post more videos starting on Monday, covering angular momentum and a few topics related to conservation of angular momentum. So thank you very much. I hope you're all safe and healthy and happy. and I'll talk to you soon. Thanks.